Welcome back to Learn Physics. In today's topic, we are continuing with the atoms. Okay. Last video we learned about Giger-Marsden experiment and Rutherford's atom model. Okay, and nuclear model of atom. That is, it consists of all the nucleus is at the center, and electrons will be around it, and it will be having its atom is almost hollow, and all the entire mass will be concentrated at the center. Most of the mass will be concentrated at the center, like the nucleus and all we learned. Okay, now we are going to study about what will be the energy of electron. How we can derive an equation for energy of an electron in hydrogen atom. In hydrogen atom, what will be the energy of electron? Okay, so hydrogen is the simplest atom to explain. Why? Because it consists of only one electron. Okay, so it is the simplest way of explaining about the atom. So hydrogen atom always we will consider and will be explaining the rest of the things. Okay, in Rutherford atom model we know the nucleus is at the center which has positive charge and the electrons will be surrounding it. So this positive charge is there and electron is there. So there will be a force of attraction, intermolecular force of attraction between the electron and nucleus. Okay, so this electrostatic force of attraction between this, electrostatic force of attraction between the electron and nucleus. So that is represented as Fe. Fe is the electrostatic force of attraction. Electrostatic force. Okay, F is represented as Fe is the electrostatic force of attraction between the nucleus and the electron. So there is an attractive force between these two electrons. Then these two electron and nucleus. Then why this is not coming closer to this nucleus? Why? Because it will be compensated by the centripetal force. Centripetal force. Then why it is not coming closer or the distance is not changing? Because if a force is, the electron is pulling out, trying to come out, means this centripetal force will be attracting towards the center of the nucleus. So both will be managing. Okay, so centripetal force we can write it as, what is the formula for the centripetal force? mv square by r. That will be equal to, what is the electrostatic force as per Coulomb's law? 1 by 4 pi epsilon 0 Q1, Q2. What are the charges? E only. So that is square by r square. 1 by 4 pi epsilon 0 Q1, Q2 divided by r square. From this, we can write it as mv square equals 1r and 1r will get cancelled. mv square equals 1 by 4 pi epsilon 0 e square divided by r. So what will be the kinetic energy formula? Kinetic energy of the electron equals half mv square. So it will be half into 1 by 4 pi epsilon 0 e square by r. So this one we will get it as 1 by 8 pi epsilon 0 e square by r. This is the formula for kinetic energy. Okay, next we are going to find out the total energy of the electron, isn't it? So next is potential energy. How we can find out the potential energy? 1 by 4 pi epsilon 0 Q1 Q2 divided by r, electrostatic potential energy. That what you learned in the first chapter. Okay, electrostatics you learned, right? So the same formula we can apply here. 1 by 4 pi epsilon 0 Q1 Q2 divided by r. So this will be negative. Why is it negative? Because it is acting towards the minus r direction. Towards the center it is acting. Okay, the distance between these two nuclei, this electron, these two charges, that is, it is in the minus r direction. This negative sign is due to the negative minus r direction. The distance between that will be in the negative side. we are considering. That is why potential energy is negative. Potential energy is negative. Why? Because it is acting along the minus R direction. Negative side only it is acting. Okay. Then what will be the total energy? Kinetic energy plus potential energy. That is kinetic energy we got it as 1 by 8 pi epsilon 0 E square by R, and potential energy is minus 1 by 4 pi epsilon 0 E square by R. Here 1 by 4 pi epsilon 0 E square by R is common. So here in this which is left out 1 by 2, here it is minus 1. So 1 by 2 minus 1 is minus 1 by 2. So it will be minus 8 pi epsilon 0 E square by R. So the total energy we got it in negative. Minus 1 by 8 pi epsilon 0 E square by R. What is the meaning of this negative sign? It is in the minus, negative direction. That means negative direction is it is acting towards the center. It is acting this. Electron is always bound to the nucleus. Electron therefore the total energy is acting in which direction? It is acting minus, the negative sign shows that it is in the negative direction, that is towards the center. So electron is always bound to the nucleus. That is the meaning of this negative sign. So the total energy of the electron is minus 1 by 8 pi epsilon 0 E square by R. This shows that, this negative sign shows that the total energy is, the electron is always bound to the nucleus. That is, it has a attractive force towards the nucleus. Okay, so clear now what is how we will be deriving the energy of electron. First we will be considering the electrostatic force and the centripetal force. Both are balancing each other, that is why electron can stay in their position. Then equating that, first finding out the value of mv square and half mv square substituting. Potential energy, electrostatic potential energy 1 by 4 pi epsilon 0 q1 q2 by R. Okay, then we are finding out the total energy which is negative. From that we can conclude that the electron is bound to the nucleus. Clear? So next is atomic spectra. See, atomic spectra. What is meant by atomic spectra? See, if I am considering an atomic gas under low pressure, so I am considering an atomic gas under very low pressure and I am passing electricity through it. So, some radiations will be emitting. So, atomic gas which is under low pressure and passing electric current through it. So, what will happen? Some radiations will be coming up. So, these radiations, if I am taking the spectrum of this radiation, so using spectrometer, we can find out the wavelengths of this electromagnetic radiation. So while we are studying about this radiation, we understood that it includes some specific wavelengths. Okay, it includes some specific wavelengths. So if I am taking those radiations in a spectrometer, then I understood I am getting a spectra of lines. Okay, all these wavelengths I am obtaining in a particular order. So that is called an atomic spectrum or emission spectrum. And some bright lines will be obtaining in the spectrometer sheet. Is that a sheet I am obtaining some bright lights. So this is called as emission spectra. So in this gas, if I am passing some instead of that, if I am passing some light to it, so the transmitted light, if I am passing some light to it, the transmitted light will be containing some dark lines in the spectrum. Okay, in the spectrum I can see some dark lines. So these dark lines shows all the properties of gas. So such spectra is called as absorption spectra. absorption spectra. Okay, so it will be in a bright lines will be there, so that is called the absorption spectra. Okay, so bright lines are called as absorption spectra, and this dark lines, that is called the emission spectra. So if we are studying about these spectral lines, we will be getting the characteristics of this wavelength, this gas. So, or we can say it's just like a fingerprint of this one. Okay, so what are the properties? If we take our fingerprint, we can identify who is it, isn't it? The same way we can identify the gas also. Okay, clear now? This is. So I'll tell you once more. Atomic gas in atomic gas under low pressure, they are passing electricity through it. What will happen? The radiations will be emitting. These radiations includes a specific wavelength. So these radiations are called as emission spectra, which is observed as a bright lines. Okay, that is called as emission spectra. Okay, so when the light is passing through it, the transmitted light from the gas, it includes some bright lines. So they are called as absorption spectra. Okay, clear? So next we are going to study about the spectral lines. Next we are going to study about the spectral series. Okay, like that one series of atomic spectra we learn, and a series of lines while we are obtaining. How we can identify these lines? We are going to study more about this spectral series. So for that to learn, I already told you for all atomic studies we will be considering hydrogen atom. Why? Because hydrogen has least number of atoms, least number of electrons. So we will be considering the hydrogen. So if I am considering this hydrogen atom and its spectral series, if I am considering that one, I can see that the number of spectral lines, for a first sight, if I am observing the spectrum, I will feel it is each and every lines are entirely different. But if we are observing for some time, we can understand that after a set of lines, these spectral series are repeating. Okay, so and the lines also, the line spacing also will be decreasing after a particular after some distance. This line spacing also will be decreasing. It's becoming closer. Okay, so that is the thing which we are observing in the case of hydrogen. In the case of hydrogen, the spectral series lines are decreasing as the distance increases. So we can see the wavelength of the first spectral series line will be observed in the red light region. Okay, that is called as H alpha. Okay, then next is observed in a green-blue region. Green-blue region is called as H beta. And violet region which we are observing, that is called as H gamma. This will be the series of spectral lines which we are observing. Okay, so like that, this red line H alpha, green line blue region H beta, violet line region H gamma, and like that many number of spectral lines are obtaining. So these spectral lines together we will call it as spectral series. Okay, all these lines are together called as spectral series. And there we can observe that the spectral wavelength increases. As wavelength increases, the spacing also will be increasing. That means as wavelength decreases, the spacing will be very less. Okay, so wavelength decreases, all the spectral series lines will be coming very closer to each other. As this wavelength increases, according to that spectral this distance also, spectral series distance between the spectral lines also will be increasing. So clear now this one? So this is called as spectral series. So here a Swedish teacher who called it as Johann Balmer observed that he had given empirical formula without any theory. He had given a formula for this spectral series, and he gave the formula as 1 by lambda equals r into 1 by 2 square minus 1 by n square. and he had given the value of n equals 3, 4, etc. Okay, so this n is 3, this n is the number of orbits he was mentioning. 1 by lambda equals r into 1 by 2 square minus 1 by n square. Like that, one formula he had given. N is equal to 3, 4, 5, etc. Like that. And r is called as Rydberg constant and its value is 1.09 into 10 to the power 7 meter to the power minus 1. So this is Rydberg constant. Okay, so he substituted this value and gave different wavelengths for 1 r is equal to, so the orbit, the spectral series which is coming to the second orbit, or will be from third orbit to second orbit. If the spectral lines are coming, wavelength will be like this, or fourth orbit to second orbit if the electrons are coming, this will be the wavelength. Like that, he had given the first formula. Simply through some calculations, he gave the formula as 1 by lambda equals r into 1 by 2 square minus 1 by n square, that is n is equal to 3, 4, etc. And this series of spectral lines which we are obtaining is called as Balmer series. Okay, this is Balmer series. After that, many series observed like Lyman series, Paschen series, Brackett series, and then Fun series. Like that, many series we observed. In that, here as per Lyman series, that is 1 by lambda equals r into 1 by 1 square minus 1 by n square, where n equals 2, 3, 4, etc. And in Lyman series, it is 1 by lambda equals r into 1 by 3 square minus 1 by n square, where n equals 4, 5, 6, etc. In bracket series, 1 by lambda equals r into 1 by 4 square minus 1 by n square, where n equals 5, 6, 7, etc. And in Fun series, 1 by lambda equals 1 r into 1 by 5 square minus 1 by n square, where n is equal to 6, 7, 8, etc. So this is the spectral series obtained in this. Different scientists had given this names. So always remember, like it's in order you should remember. Then the empirical formula will be in order in the sense, first you can remember about Lyman series, then Balmer series, then Brackett series, Paschen series, then Brackett series, and then Fun series. Okay, these formulas you can ask in this numerical type of questions, that is 1 by lambda equals r into 1 by 1 square minus 1 by n square, and here it is 1 by lambda equals r into 1 by 2 square minus 1 by n square, and here 1 by lambda equals r into 1 by 3 square minus 1 by n square, and here it is 1 by lambda equals r into 1 by 4 square minus 1 by n square, and here in Fun series it is 1 by lambda equals r into 1 by 5 square minus 1 by n square. So here what will be the value of n here? 2, 3, 4, 5, etc. Here in Balmer series, n is equal to 3, 4, 5, 6, etc. And in Paschen series, n is equal to 4, 5, 6, etc. And this Brackett series, n is equal to 5, 6, 7, etc. And in Fun series, n is equal to 6, 7, 8, etc. Okay, that will be the this empirical formulas for finding out the series of spectral lines. For remembering that, I will give you a clue. Usually I will tell my children to remember like that. Libaba BP, Lyman, Balmer, Paschen, Brackett, Fun. Okay, that's what my teacher taught me in this way. Now still I am remembering, so I am passing just the same thing to you also. Libapa BP, that is Lyman, Bama, Passion, Bracket, and Fund. So in series we can remember and easy to observe the spectral series. Okay, clear now? See how we will be. So if the light is emitting from the electron is emitting the radiation, and from second one to first one, or third one to first one, or fourth one to first one, if it is coming, the wavelength, how we can find out using the Lyman formula. And if it is coming to the second one, so we can use the Balmer formula. So from different orbits, if the electrons are losing energy and coming to the this previous one, or exciting energy and coming to the next one, then we can find out the spectral series like that. Understood? Balmer series, we can write it in another way. See, we know C equals mu lambda. Then what is 1 by lambda? That will be equal to nu by C. Okay, so if I am rearranging this 1 by lambda as nu by C, nu by C equals R into 1 by 2 square minus 1 by n square. So, see, nu equals RC into 1 by 2 square minus 1 by n square. Like that also we can write out. Okay. So in any format, anyway the things are same only. Frequency asking, they are asking about the frequency, you can directly apply this formula. So all these spectral series, we can use these formulas only in the case of atoms which have very less number of electrons. That is mainly for hydrogen atom we are using. Otherwise helium means if it is having a positive ion, that is one electron is lost from that, then we can use this one. Or lithium, 2 electrons are losing, then we can use this empirical formula. Otherwise, this formulas won't be working out in other cases. Okay, so I told already, this is mainly valid in the case of hydrogen spectra or hydrogen related. 1 electron means we can use this formula. Okay, understood?